Hello everyone, I'm pleased to have the opportunity to present our paper outdoor sound propagation based on non-adaptive FDTDP. Next, we will introduce from 5 aspects: introduction, related work, method, experiment, and conclusions. First, introduction. Realistic simulation of sound propagation can improve users' immersion in games or VR outdoor environment or accounts for large parts in the virtual environment. Therefore, realistic simulation of outdoor sound propagation is necessary. Some research have proposed sound propagation techniques that can be applied in both outdoor and indoor scenes. However, these techniques do not consider the two key factors affecting outdoor sound propagation: the inhomogeneity of the outdoor atmosphere and the grid effect. In this paper, we propose an adaptive FDTDP method which can quickly simulate sound propagation in outdoor inhomogeneous atmospheric scenes with an abundance of grid. Second, related work. Outdoor sound propagation has been widely studied in the field of acoustic. The methods of solving the problem of outdoor sound propagation include numerical acoustic method and geometric acoustic method. Numerical acoustic methods calculate sound propagation by numerical methods to solve wave equations including FFP, FDTD, and FDTDP. FFP and P are frequency domain methods. These methods are accurate but slow. Geometric acoustic methods including Gaussian beam method and ray tracing method, which calculate the speed is fast, but the low frequency domain cannot be simulated. In computer graphics, sound propagation simulation needs to be fast enough to interact in VR and games. However, in the field of acoustic, it is difficult to achieve interaction with sense. Interactive sound propagation simulation often uses computation to obtain the acoustic kernel of a static sense, and take this kernel to calculate the pulse response function of the moving length, direction, and runtime. Also, some of these methods, ARD and the equivalent source method, could be applied to sound propagation in outdoor atmosphere. They did not take into account atmospheric inhomogeneity, the grid effect, and low reflection. And the method. As seen in figure, the algorithm is divided into 3 stages: simulation, encoding, and sound rendering. In the simulation stage, we propose an adaptive FDTDP method to simulate sound propagation in outdoor scenes. The 3-dimensional space is divided into a series of 2-dimensional planes. According to the location information of sound source and obstacles, we decompose the 2-dimensional planes into the near-source complex regions and the far-source regions. We build an adaptive FDTD solver to simulate sound propagation in near-source complex region and an adaptive PE solver in far-source regions. In the encoding stage, we specially designed an encoder to process the sound pressure data of outdoor sound propagation, which can greatly reduce the memory of sound pressure data and simulate outdoor sound propagation more accurately. For the near-source complex region, we extract ER in frequency domain from sound pressure data and set the corresponding time of DR to 0. For far-source region, we first transform the frequency domain sound pressure data into time domain. and then we do the same encoding as near source complex region. Finally, we decide the function to feed the sound pressure data. In the sound rendering stage, according to the listener's location, the decoding method is selected to a built-in ER and IR. In far source regions, where a built-in the IR and listen the position by the fading function, the intentional ER and the intentional IR. Finally, auralization is related in the frequency domain. Next, we will introduce every stage in detail. In the simulation stage, in order to use FDTD-PE method to simulate three-dimensional scenes, we first provide the three-dimensional space separational and liberational, as shown in figure. In figure A, because the PE methods depend on the propagation direction of sound waves to simulate, we transform the sense information from rectangular coordinate system to the cylindrical coordinate system. The three-dimensional space is decomposed into n planes, as shown in figure B. According to the FDTD-PE plane partition theory, AG is decomposed into complex near-source region BG and two far-source regions CG and CG prime. And we extract the growth change curve HR prime from the sense information of AG, as shown in figure C. Next, each plane is calculated. We determine the simulation time length Tg of FDTD method, and the time single of sound pressure in BG region is calculated by FDTD solver. At the junction of BG with CG and CG prime, FFT is used to convert the time domain sound pressure single into the frequency domain, which serves as the intention fields. After determining the error size, use PE solver simulation. The CG and CG prime regions are simulated by the PE solver. Here is the equation for Tg and L prime. Tg is time length of the impulse response calculated by the FDTD method in region BG. R1 is the length of region BG. R2 is the total length of the area with obstacles in BG. It is unnecessary to calculate the sound pressure value in all areas of CG. We only need to calculate part of the sound pressure data for fitting. We assume that the height of region CG is h and the length is l. Here is the formula we used. In the encoding stage, we needed to sample and encode the sound pressure data to reduce the use of memory space. We input the sound pressure data of region AG. First, the data is proposed by downsampling, and then the IR is gotten. In BG region, we extract the peak value of time domain sound pressure single to IR. Then IR is separated into ER and IR. ER of each sampling point is saved. After increasing the peak dysentery at the sampling point, IR is converted to the frequency domain for saving. In CG and CG regions, the frequency domain sound pressure data is converted into time domain. Then we get ER and IR by using the same method as that in region BG. Next, experiment. We tested our method in these three representative outdoor scenes. The performance of our method was compared to other state-of-the-art methods as shown in table. As shown in figure, in the same sense, we simulated the sound propagation of regional growth and porous medium growth, respectively. According to the experimental results and characteristics of various methods, we compared our method with FDTD-PE, FDTD, and PE in terms of memory, computing speed, and applicable scenario type as shown in table. To further assess the realism and accuracy of sound results by our method, we designed the user study. We show all our questions and the results of user study in figure. Finally, conclusions. There are three main contributions of this work, including an adaptive FDTD-PE solver, a function fading encoder, and an function sound rendering method. That's all for my presentation. Thanks for your listening.